All right, well, thanks for joining us, everybody. You are tuned in to Boise State Physics First Friday Astronomy event. My name is Brian Jackson. I teach physics and astronomy here at Boise State. For those of you who are just joining us for the first time, welcome. The First Friday Astronomy event is a monthly lecture series. We bring in a space scientist of some stripe. Sometimes we bring in astronomers, sometimes we bring in space policy folks. We brought in science journalists as well. So it's a wide variety of folks who come in to talk to you about space science in one form or another. It takes place on the first Friday of every month. That's the first Friday of every month. We host an astronomer or a space scientist of some kind. This is, of course, the first Friday of November. And so we're very fortunate tonight to have Dr. Johanna Teske here. I'll talk to her about her in just a moment. But to give you a sense for what's coming up, our next event will be on December 3rd, always at 7:30 p.m. Mountain Time. We're going to be very fortunate to have one of our own, Tyler Gordon, who is currently a graduate student at the University of Washington. He's actually a Boise State physics alum. He's going to talk to us about his work looking for exomoons. So these are moons in other solar systems. So that should be a really interesting talk. This lecture series is entirely supported by public donations. We don't get any funding at all from the university, from the state. This is just paid for by folks like you. And so if this is something that you're interested in supporting, we encourage you to donate at boi.st/give-to-astronomy. And I'll put that link in the YouTube stream so you can see it there. We would appreciate anything you can help us with. Your donations have in fact allowed us to purchase a digital mobile planetarium. And I'm just going to show you a picture here. We were very fortunate to have a local Girl Scout troop come in a couple of weeks ago and actually use the planetarium for the first time. So here you can see, this is me, I'm standing here, this goofy guy right there. Here's our planetarium dome. And then here's our Girl Scout troop who's visiting with us. This is a little bit different from other planetarium domes you might be familiar with. Sometimes planetariums, of course, are buildings that you can go into. Those are nice, but they're not mobile. You have to come to the planetarium. Other planetarium domes are actually kind of like inflatable tents that you crawl into on your hands and knees. Those are really good because they're very immersive. But one challenge with those is they usually need a very big space, and they're not very handicap accessible. It's harder for folks who have some disability to crawl into the dome. This dome that you see here pictured, it has all the same kind of equivalent capabilities, but it allows you to just sit in a normal chair and see the sort of view-filling projection that you would usually see in some other kind of dome. And so your donations helped pay for this. And so we're very excited to introduce this planetarium in our upcoming shows. The plan right now, COVID willing, is to begin to host these First Friday Astronomy events in person again, starting in January. And so we've got a really rich schedule of talks coming up for you in the spring, which we hope to be able to host in person on campus, and we hope to be able to introduce you to this planetarium. So again, if this is something you're interested in, you want to help to support, I would encourage you to go to boi.st/give-to-astronomy, and you can donate to help support these programs. Okay, and with that, I'm going to introduce our speaker for tonight. We are extremely fortunate to have with us Dr. Johanna Teske. Dr. Teske received her bachelor's degree in physics from the American University in Washington, D.C. She then went to the University of Arizona, where she was a graduate student. And we overlapped for a little bit, so I'm very humbled to be able to say that I was in the cohort with Dr. Teske. She earned her PhD in astronomy, studying planet formation with Professor Caitlin Griffith and Professor Katja Cunha. She recently joined the Carnegie Earth and Planets Lab, which is a very prestigious research institution there in Washington, D.C., as a research scientist. And she's we're going to hear tonight about some of her really exciting research using the soon to launch James Webb Space Telescope, JDBST. So with that, I'm going to let Dr. Teske take over.
Great, thank you. All right, I need to share my screen. Here we go. That. All right, see everything okay? All right. So welcome everyone. Good evening. I'm delighted to be here with you in mind, if not full body. In this talk, I'll start with a brief and definitely incomplete overview of just the current landscape of small exoplanet demographics, specifically how and what do we know about the diversity of their compositions. And then I'll outline what I think are a few exciting prospects on the very near horizon as we move farther into the era of exoplanet characterization. You're attending this talk at the perfect time because on Thursday we heard the much awaited plans for the next decade plus of astronomy in the US, which I'll touch on at the end of my talk. All right, so first, just to set the stage, in these plots, I'm showing kind of a few different maps of exoplanets, if you will, or exoplanet demographics. So these are planets orbiting other stars. And the two plots show their orbital period in days on the x-axis versus either their radius in Earth radii or mass in Earth masses. And as you can see, we now know of a large and diverse sample of other worlds. And those that we have found so far are mostly not like the solar system planets right here in sort of a reddish orange color. And actually this plot doesn't go quite to long enough periods to get to Neptune and Uranus. So tonight I'm going to focus on composition, that aspect of demographics, although one could also talk about exoplanet demographics across architectures in the systems, orbital dynamics, types of stars, etc. So, but I don't have time to cover all of that tonight. So let me walk you through how we try to measure planet compositions first. All right, so for interior compositions, we get constraints on the bulk density of the planet. And so that can tell us a little bit about kind of what the bulk composition would be. If we have measurements of the planet masses and radii, like I described in the previous slide. So this is just a kind of cartoon representative model of a planet, but it's just a model. We don't know if they actually look like this on the inside. So I'll start by talking about mass. Planetary masses are primarily derived through what's called the radial velocity or Doppler wobble technique, where we observe the very small changes in a star's orbit. So this is the star and the planet is going around. We measure these changes due to the interaction the star has with the orbiting planets. So we think of the star as just being at the center and the planet going around, but the planet tugs on the star just a little bit too. And that produces these changes in the star's velocity, which then affect the light that we observe through the stellar spectra. So these dark black lines represent the star moving back and forth and different absorption lines in the star's atmosphere that we can measure. Those details aren't super important. The thing to maybe remember is that very close in planets to their host stars, hot Jupiter exoplanets, like the size of Jupiter, but orbits much closer than Mercury, they have these radial velocity signals in the tens to hundreds of meters per second. That's usually the unit that we use. Whereas Earth induces a signal of 9 centimeters a second on the sun. So very challenging to measure that type of signal. And in fact, we can't do that yet. That's aspirations to hopefully come in the future. All right, so next we measure the planet radii primarily through the transit technique. And this was used by the Kepler space mission, if you've heard of that, to find thousands of new planets around other stars. And so as you can see in this video, here the planet passes between the observer and the star, periodically blocking out a little bit of the stellar light. In this case, hot Jupiter, those giant close-in planets have transit depths around 1%, whereas the Earth around the sun, as you would imagine, has a much smaller transit depth of less than 1/100%. And these are measurements that can be made from the ground. Our radial velocity measurements are often, they're only done from the ground right now. But transit observations are also often happening in space. And so I'll come back to those as well. Our constraints on exoplanet atmosphere compositions come mostly from those same type of transit observations, but instead of just observing at one color, or one wavelength, we disperse the light and look for changes in the atmosphere of the planet as a function of wavelength. So let me dig into that a little. So the transmission spectrum is measured at this part of the planet's orbit as it crosses the front of the star. And as light filters through, starlight filters through the planet's atmosphere, it is absorbed preferentially by whatever molecules are in the planet's atmosphere. And so they leave their fingerprint on the light, and then we can detect the composition of the atmosphere. And this is basically the transit observations are most sensitive to the scale height. And so in this equation, you have the temperature of the planet, its gravity, a constant, and then this letter mu here corresponds to the mean molecular mass of the atmosphere. So lighter atmospheres are easier they have bigger signals, they're easier to detect. Let's see, yes, that's what I wanted to say about that. So then this is kind of cool. When the planet goes behind the star, you might think, well, we don't see anything. Like, why is that useful? But it is literally, if you take star plus planet and then subtract just the star, you get just the planet. So the emission spectrum represents the reflected light and thermal emission from the planet when it's directly behind the star. So it's day side. And these observations, as you might guess, are sensitive to that temperature of the planet and also the albedo or the reflectivity of the planet. And then you can combine these two types of observations, which is pretty cool, and just monitor the planet throughout its entire orbit around the star. And that's called a phase curve. And those types of changes can really give you more multidimensional picture of what's happening on the planet. You can see potentially the transport of heat from the hot side to the cooler night side of the planet. And this can help reveal the presence of clouds and even the cloud composition if the planet has clouds. So now you have your experts in how we measure planet composition. So returning to this plot, we have these few rough categories of exoplanets. Astronomers like to categorize things, as I guess many scientists like to do. And in my talk title, the small that I'm referring to is kind of in this region of the plot. So lava worlds, rocky worlds, I'll talk about these, but it also includes these mini Neptunes or super-Earths, which I think are particularly interesting because they fit into this space between rocky and ice giant worlds, unlike anything that we have in our solar system, right? They're sort of in between Earth and Venus and Neptune and Uranus. So I'm going to refer back to this plot a couple of times to kind of orient us and describe a few subpopulations of planets. So let me explain it first. So here I'm plotting the planet radius versus mass. And all these points it's a subsample of that plot that I just showed, but this is just planets with both of these measurements. So in many cases, we only have the mass or we only have the radius. So this is a subset. And as I said, with these measurements, we can estimate the bulk density and then compare that to these different colored curves, which are theoretical estimations of what planets of these different compositions would look like, which range from something like pure iron to rock and water to pure water. The symbols in the background, kind of the square symbols, are just planets that don't have as precisely measured masses and radii. So the bold points are more precise. And the pentagon symbols, which you can see a few of, those are actually planets whose masses were measured using a different technique that I didn't talk about. They're not radial velocity masses. They're called transit timing masses, and that's a different way to measure the mass. It depends on interactions between multiple planets in the same system. But those are not details you have to remember. And the bold outlines are planets in multi-planet systems, which you can see many of them are. All right, that's just orienting. And before I start digging into this, and I should say the temperature the color is the temperature or flux that the planet's getting from its star. So redder in this color bar is cooler and yellow is hotter. I do want to just make clear that this is not what we call an occurrence rate diagram. So this is just raw counts of planets, not corrected for any observational biases, which, as you may have noticed, as I pointed out in the first plots, it's harder to detect planets that are at longer orbital periods. And so many of our detections are at quite short orbital period. So there's kind of ways to try to tease out what the total demographics would be, the occurrence rates, but this is just raw counts. So it's still interesting. So let me highlight a few interesting subpopulations. So this is the one that I was just talking about, planets between the size of Earth and Neptune. And you can see that they sort of have a spread here. So what's up with that? Like, what are these planets? What are they made of? What do we know about them so far? So there have been a few suggestions for how these planets were formed based on their radii, and orbital period observations. And so this is a important plot in my field right now. So it's showing, this is an occurrence rate diagram. So this is the frequency of the planet versus its radius. So lots of planets are included in this plot. And you can see that these two sizes of planets are the most common, the most frequent between Earth and Neptune. And then the frequency of giant planets is sort of trails off. It's much less. So, but this is not, only one peak. There seem to be two, maybe bins of planets here. And it's thought that this is due to some sort of mass loss in the planet at early stages. So this could be due to high energy radiation from the star driving off the primordial atmosphere of the planet, or it could come from internal heat, thermal energy continually heating and inflating and driving off primordial atmospheres. And by primordial, I mean things that were accreted when the planet formed out of the dust and gas around the star. In both of these scenarios, the planets have a common origin, but then end up either as a sub-Neptune or a super-Earth with kind of very little leftover atmosphere. Recent work has suggested maybe some of these super-Earth planets can retain small amounts of their primordial atmospheres. So maybe there's a third flavor in there, but basically they all start the same. Now, interestingly, the radius measurements of these planets, when you combine them with models of formation and evolution, have been interpreted as suggesting uniformly Earth-like compositions of these planets. So how do they get that? Well, the observations, this very famous plot, are not well matched with a model that assumes all the planets have iron-dominated interiors, nor a model that assumes that they have interiors dominated with water or ice, but a model that assumes a silicate, sort of rock-dominated interior does a pretty good job at matching this double-peaked distribution. And actually, this diagram has become so canonical in my field that you can buy stickers of it to put on your laptop or water bottle. So you can check those out if you want. So this suggests that maybe there's not a lot of variation in these planets' compositions, in internal kind of the rocky part of their compositions. But the radius might not be telling the whole story, as you may have guessed. from my previous plots. So showing this one again. To first order, like I said, you need density to measure the composition of the planet. And in this range, or in this, for these super-Earths and sub-Neptunes, they sort of span at any given mass. There's a span in radius, and any given radius, there's a span in mass. And so that sort of suggests a range of potential bulk compositions, as you can see by them spanning these colored curves. And so how did this variety come to be? Are there really multiple formation pathways? Mass is a key factor in helping us understand this. So we're starting to try to learn more about this population from that sample that has both masses and radii, like those in this map that I've been showing. And so this was a study that took a subset of those mass plus radius planets and tried to fit them with a statistical model that had different subpopulations of planets, gaseous planets, evaporated cores, but then also this population of intrinsically rocky planets that just formed rocky. They didn't start as a gas enveloped rock. They just didn't have large envelopes to begin with. So that's kind of interesting that this is their best fit model. It's a little bit hard to tell from this diagram, but I assure you that was the conclusion. And then on the more theoretical or physical side, some studies have shown that the population of sub-Neptune planets, kind of 2 to 4 Earth radii planets, can be explained by models with roughly a 50-50 mixture of rock and ices or water, with variations in the water abundance accounting for the range of sizes and densities for these planets, instead of just differences in the fraction of hydrogen gas atop the rock. So if ices or water are incorporated into these planets, it might point towards accretion of that material from beyond the ice line, so the position in the disk where water freezes out, versus all these planets and all their things that go into the planets forming just very close into the star. And so that could potentially mean different formation pathways for these planets. Oops, where's my mouse? Here we go. So this is all interesting. I think we still an open question, and I'm actually investigating this with something called the Magellan Test Survey, or MTS, not very creatively named, but it does the job. And this is measuring the masses of 30 planets detected by this new space telescope, fairly new, it was launched a few years ago, called TESS, Transiting Exoplanet Survey Satellite. And TESS gives us the radius, and then we use one of those radial velocity spectrographs to measure the Doppler wobble in the star to get the mass of the planet. And the motivation is really to not just find and measure their densities, but we want to dig deeper and investigate whether super-Earths and some Neptunes really did form along the same or different pathways, and look at that empirical relationship between the radius and mass of the planets. Is that different for different populations of planets? And does it depend on other properties of the planetary systems besides just bulk density? So sort of thinking of adding an extra dimension out of the plots or out of the page for the mass and radius graphs. And those extra dimensions we think might be important are the insolation flux, how much energy the planet is receiving from the star. That is obviously tied to the mass loss, but there's the mass loss obviously depends on the mass of the planet. And so that's why we think masses are important to measure here. Host star composition seems to be related to the types of planets that form, but not necessarily in very obvious ways, at least for small planets. And so we want to investigate that more as well. And then system architecture, by which I mean, are there other planets in the system that tests didn't necessarily detect, maybe giant planets farther out that might have impacted the formation of the smaller planets. So that is my ground-based survey. So that's the super-Earths and sub-Neptunes. Moving to this part of the diagram, we have fewer precisely measured planets in this terrestrial regime, and many of them are actually around the same star. All these pentagons are around one star called TRAPPIST-1, which you may have heard of, and I'll come back to that system. But notably, all these small planets cluster around this sort of greenish or yellowish lines, indicating an Earth-like mixture of rock and iron. And while several planets that are smaller than about 1.5 Earth radii and more massive than Venus appear to be less dense than rock and might have large volatile envelopes, there just aren't that many cases with densities higher than an Earth-like mixture of metal and rock. Despite actually detection bias towards detecting more massive planets at a given size. At a given size, if you have a more massive planet, it will produce a larger that radial velocity signal. And so it would be easier to detect, but we don't see them. So Earth-like planets, in very big quotes, right? This is a very broad brush. My geologist friends would not agree that they are Earth-like, but Earth-like in this sense, planets might be more common than Mercury-like planets, which is very, very dense planet. So I think that's interesting. Of course, like I said, these planets are substantially not like the Earth because they're so much hotter. But for those that are at very short orbital periods, things like 1 day or less, they're going around their star. And are thus just so highly irradiated, they might serve as kind of a Rosetta Stone for the interiors of their larger, less irradiated cousins. And so these ultra short period USP planets are so strongly irradiated that they really should not have any primordial atmosphere left. And you can directly constrain the composition of the rocky core without worrying about the potential degeneracies in trying to model both the core and an atmosphere, or the core and an atmosphere and some sort of water envelope. These planets, so I was going to highlight a few of them in this plot. And they also sort of fall as an ensemble around this green line here, which is an Earth-like composition, but there are these few outliers, which I think are interesting. So they're slightly large or slightly underdense. And I think that's worth noting because all of these planets orbit stars that are have more metals, so not hydrogen and helium, basically everything but hydrogen and helium, astronomers call metals. And so these stars have more metals than the sun. And at least in the case of 55 Cancri E and WASP 47E, they also host a close-in giant planet, which may be influenced like the movement of dust and pebbles in the system, and maybe thus influence the water inventory of the inner disk where the small planets were forming. And so I think it will be interesting to see if more of these systems pop up, and maybe their compositions are substantially different than these other USPs, and that could be due to other planets in the system. So I'll be watching that space. Finally, I did want to just set the stage for the future landscape part by showing a little or how little information we have about these planets' atmospheres, even less than their masses and radii. So this is the same plot, but now I have blue stars around the planets for which we have those transmission spectra, so the light coming through the atmosphere, planets in front of the star, from the Hubble Space Telescope around the 1.4 micron, so a near-infrared water feature. So unfortunately, in this small sample, many of the observed spectra are flat at the level of measurement precision. So this is that case of the TRAPPIST-1 planets. Again, I'll come back to this system in a little bit more detail, but it has 7. So one of them is not shown here. 7 small planets. And it's a very, very cool star. And so that means that the signals that the planets produce, the dip the planet makes around the star, even though the planets are very small because the star is also small, we were able to detect them. These are really our best examples of really terrestrial rocky planets. And these previous observations of the atmosphere, so the observations are the black dots in all these plots, and then the colored curves, which are sometimes binned to match the observations. Those are all different models of atmospheres that they were trying to match to the observations. And you can see that they just don't really match. So these observations rule out an atmosphere that is largely dominated by hydrogen, and the authors here don't expect these planets to have hazes, which, as I'll show in a second, that can block light coming through the atmosphere and also cause a flat spectrum. But even though these spectra are flat, basically the take-home message is that that's actually not surprising. We don't necessarily think they're going to have big atmospheres because these are small planets, and several of them are actually in the zone around the star where liquid water can exist on the surface. And so these observations actually support these planets' terrestrial and maybe even potentially habitable, also in big quotes, nature. So the featureless spectra for planets that are larger and thus have gaseous envelopes, like it's kind of shown in this example, these flat spectra, again, the observations are in black dots, can be explained by the presence of thick aerosols at high altitudes obscuring our view of the bulk of the atmosphere. So we can't constrain the composition because we can't see farther down. And these are particularly pernicious for super-Earth and sub-Neptune planets because many of them are cooler, and so that might enhance the formation of these aerosols, which really seems to be the case for this. This is like our canonical example of a small planet, GJ1214b, and these are observations that really just show very little spectral variation. In this case, GJ1132b, the featureless spectrum could point towards a cloudy hydrogen-dominated envelope or just a very, very small atmosphere or no atmosphere. So it's hard to tell. We have a few examples of these flat spectra. Despite those flat examples, there are still still small, but growing number of exceptions that are not flat. Although in such a small sample, it's hard to know what is the rule and what is the exception. One example is 55 Cancri E, which is one of those ultra-short period planets that I mentioned. And there were some observations, so this is a zoom in here, that showed maybe some variation. Maybe you can match it with a model that has a high ratio of carbon to oxygen in the atmosphere. But this hasn't, we would need more observations sort of at these longer wavelengths to confirm that. And other ground-based observations sort of are in a little bit of contrast with these observations. So it's just hard to tell. This was also a planet that had some of those secondary eclipse and phase curve observations. And that actually suggests maybe variation on the surface that pointed towards maybe it being a lava planet. So I'll come back to that as well. Here we go. And then thus far, probably the most, one of the most exciting, it's hard to pick, detections in the last couple of years. This is the smallest habitable world planet, habitable zone planet with confirmed water vapor detection. So this is Kepler or K2-18b. And this, the author's modeling of this water feature here, also from, I keep losing my mouse, HST spectra. That suggests that the data are best matched by a hydrogen-dominated atmosphere, but with water vapor absorbing above clouds that are in the middle of the atmosphere. And this is particularly exciting because this planet receives about the same amount of total insolation flux from its host star as the Earth does from the sun. So this seems to have resulted in the right conditions for water vapor to condense and explain the clouds that they've detected, or that the observations point towards there being. And then finally, this is another example of a small planet, a rocky planet, with a fairly cool temperature as well, in the conservative habitable zone of its host star. But these observations are, as you can see, compared to these models, just lower quality. It's harder to tell what's going on. So they have a tentative evidence of water, but this paper also shows a few different types of features on the surface of the star that could also be causing the signal that they see. You can see none of these are a very, good match, but showing that the amplitude of what they're seeing in the transmission data might actually be due to modulation on the star's surface. So this is going to be tricky moving forward, making sure that we're measuring changes in the planet's atmosphere and not the star's surface. For very cool stars, they can actually have things like water in the atmosphere of them as well. There are a few additional planets that also show changes with wavelength in their spectra, but it's not always clear what the origin of that change is, and there are trade-offs and using different parameters to model it. So there's just lots of degeneracies. So we really need to move out of the low number regime and get more data on more planets. And so, as you might guess, that is what's coming. Enter NASA's newest flagship mission, the JW Space Telescope, which focuses on observing at infrared wavelengths from space. Its primary mirror is 6.5 meters, so a little over 20 feet. And it's made of beryllium coated with gold, you can see in these videos. It's going to orbit at what's called the second Lagrange point, or L2, as you see labeled there. And that lets the telescope stay in line with the Earth as it moves around the sun. And the telescope has several just amazing new innovative features, like this folding segmented mirror, which you just saw in the other video, and will pop up here as well. And then this deployable 5-layer sun shield that's about the size of a tennis court. And both of these unfurl after the telescope launches into space. The sun shield is there to keep the telescope and the instruments extremely cold, below about minus 370 degrees Kelvin, to protect the telescope from external heat. And it will always be between the sun, earth, moon system and the telescope. So that will protect the instruments behind the primary mirror and enable them to function. All right, as I mentioned before, the exoplanet detections with Hubble have been mostly in this water band. There's also been some optical detections at kind of low resolving power, by which I mean how finely you're sampling the spectrum. And so you can see red is just not many points as a function of wavelength, and then orange is a little bit more, and yellow is even more. And that's better if you're really trying to distinguish between these different features that are caused by different molecules. All right. Enter JDBST, right? We are getting a little bit of information here about water, but these different instruments on JDBST probe all these other molecules and also at different resolving powers, so enabling us to get different levels of detail about the abundances of these molecules. And so this is just gonna totally break open our ability to understand these planets in detail. There's lots of different options and ways to use the instruments to get the molecules that you want. For the aficionados, the dotted and dashed and solid lines are just different orders of the spectrum or filters or gratings that you can use. Getting to the science of what JDBST will do, which is also just, this whole process is pretty mind-blowing. In terms of exoplanets, JDBST will investigate all these different stages of planet formation and evolution. Yeah, I don't have time to go into all of them, so I'll just hone in on the theme of my talk, which are these fully formed and small planets. And so first up are the SuperEarths and mini Neptunes that I talked about before. And there are several programs that will focus on, again, those transmission spectra of fairly small planets around nearby stars, so more on the super Earth or even terrestrial regime. And one program in particular is going to focus on stars around the closest and smallest, planets around the closest and smallest stars, so M-dwarf planet systems. And these are important to understand because for the next few decades, these M-dwarf planet systems, the ones that are closest to us, represent really our best chance at characterizing potentially habitable planets in the full scope of that word, right? There's a lot we don't understand about habitability, and these are an opportunity to try to tease out how that depends on planet size and composition and the radiation you're getting from the star. M-dwarf stars are typically more active than the sun, a solar type star, so we're not actually sure how good of environments there'll be for life. But that's one of the things this proposal is trying to start to answer. There are some programs for observing the day sides of planets, the secondary eclipses that I talked about, as another way to measure whether they have atmospheres, and if not, the surface compositions of those planets. And there's also a full phase curve observations of our favorite GJ1214b. And so that is going to really help. It'll get the behind the star spectrum, emission spectrum, as well as the transmission spectrum in the mid-infrared, whereas the Hubble data was in the near-infrared. And so this will finally reveal the composition of this planet's atmosphere that we haven't understood because it's been blocked by clouds or aerosols. So that will be really exciting. And JDBST will also revisit our friend K218b to help pin down whether it's a planet with a large, whether it has a large hydrogen-dominated atmosphere, or whether it's an ocean planet with a thinner atmosphere. These are things we're not quite sure of yet, even given the really nice HST data. Or, as this paper suggests, maybe something in between. So this is a simulation. This is not actual data. But this paper was making a prediction of what K218b observations could look like if it's a Hycean world. And that is something with a large hydrogen atmosphere, but also an ocean. And the paper suggests that maybe that ocean underneath a big atmosphere could still host microbial life, like the extremophiles, that we find in the deep oceans in our planet. And so there's a couple programs really trying to understand what this planet's atmosphere is made of across a much wider wavelength range than was possible with HST. And I can't leave this section without mentioning my own program with JDBST, which just happens to be the largest in terms of number of hours and I guess number of targets. The largest exoplanet program selected in this first round of cycle 1 guest observer proposals. And this was really motivated by that Magellan test survey that I'm doing to get the masses of planets and really investigate the formation of small planets in a more robust way, right? Using those extra dimensions. Besides getting the masses and densities, clearly a critical component to understanding these planets is understanding their atmospheric compositions, which can have different origins, as shown in the figure here. And so namely, they can have, as I've been talking about, primary atmospheres accreted from the protoplanetary disk, or secondary atmospheres, perhaps of more varied compositions that have been outgassed from the interior of the planet. And actually, some recent theoretical studies suggest both super-Earths and some Neptunes might experience these interactions between the interior and the atmosphere, giving us insight into what is in that mantle, or the magma, what was in the magma ocean of the planet. And so that can give us a new perspective in planets. We can't send probes to these planets, right? They're too far away. But maybe by studying their atmospheres, we can learn something about the interior of the planet. So I'm really excited about our proposal and the awesome team that we put together to do this. We'll be using the NIRSpec instrument that I showed. So getting 3 to 5 micron transmission observations, and really trying to jumpstart the study of small planets with JDBST. Our program has 11 planets, and the data will go public right away for everyone to get to use. All right, so those are the super-Earths and some Neptunes. Coming back to our demographics, I wanted to highlight a few more cases. We have hot rocks, which I mentioned as ultra-short period planets. So JDBST is going to look at the phase curve. So again, as the planet goes all the way around the star of our friend 55 Cancri E, to distinguish whether it has a thick atmosphere, it has an atmosphere, or maybe some sort of rocky or mineral-dominated atmosphere, and investigate that variability of the day-side emission, whether that's dependent on atmospheric properties or surface features. And then there's this new ultra-short period planet called K2-141b that also might have like an exotic outgassed atmosphere, and we'll be able to see whether the surface composition is different from those planets in our solar system. There's another planet that's being revisited. They're all, they've been detected before, but some of them also have additional space-based data from previous observations. This is from Spitzer observations. So these are also near-infrared observations. This is what a phase curve, looks like. And in these observations, this is just at one wavelength, but the authors use that to suggest that the surface of this planet has a basaltic, kind of from volcanic eruptions type of crust. And so this planet's going to be observed again with JDBST to get even better constraints, and maybe even trace amounts of like if there's sulfur dioxide that is from ongoing volcanic outgassing, that might be able to be detected by JDBST. So this could really provide our first hint at empirical constraints on a geologic history of a planet. That's pretty cool. Then I said several times I come back to the system. Well, yeah, here we go. Since the discovery of these 7 planets orbiting this, what's called an ultracool dwarf. So you can see this is a blow up of the inner solar system. This is the relative size of the sun versus the TRAPPIST-1 star. It's actually not so different in size from Jupiter. And this system has been suggested as sort of analogous to Jupiter and its moon system. The planets are in this complex chain of resonant orbits, and they're all similar in size to the Earth, a little bit bigger or even a little bit smaller. E, F, and G, these planets are considered to be within the habitable zone around the star, and so they could have liquid water on their surface. And so anyway, this is just a very exciting system. I also love this. There's a few different visualizations, and this was, maybe you'll be able to hear it. Hopefully, this is one of my favorites. Which is actually built by this like hot pop robot maker family. Point being, this is going to be a wealth of information about terrestrial planets around a very different type of star, but again, they're sort of our best shot right now. And so this is another simulation of the types of two different types of atmospheres that one of the planets might have, something that has oxygen but not very much water, versus something that's been outgassed. And JDBST is just going to totally clean up on these planets. It's observing transmission and emission and many different wavelengths. And so this will be a very well characterized system, multi-planet system in the next few years. And then finally, I just also wanted to quickly mention, I didn't get to talk about these before, but these very interesting planets called SuperEarths, or sorry, SuperPuffs. And so you can see they're kind of outliers in, again, this radius and planet mass space. And they're large radii challenge models of planet formation evolution because they shouldn't have kept their atmospheres. They have big atmospheres, and those should be vulnerable to atmospheric loss, which makes their continued existence kind of a mystery. One solution is that they're actually enshrouded not in kind of hydrogen helium gas envelopes, but high altitude haze layers that make them look bigger than they would if they had clear atmospheres. And that's what a proposal from Peter Gao, my colleague here at EPL, is trying to investigate. There was also a suggestion that maybe the reason that they look bigger than they actually are is because they're enshrouded in, they have rings like Saturn. And this was proposed by some other colleagues. But JDBST will start to give us a little bit of hints about the nature of these planets. So that will be something else to look out for. They're not very common, but the weird or unique planets are also interesting to study. All right, that's just a taste of what's coming in the next few years in the study of demographics of small planets. We're eagerly awaiting the launch of JDBST. It's scheduled for 7:20 EST on December 18th. So set your calendars if it doesn't get moved. And that's happening from French Guiana on an Ariane 5 rocket. And it's doing that it's launching near the equator because the spin of the Earth can help give it an additional push. So this is a slide from almost a month ago. So I think we're more like in here in the timeline. But you can see even after the launch, there's a period of commissioning and checking everything out. And then, will be something like 200 days before we start taking science observations. So still a little while to go, but it's starting to really all come together. It's been a long time coming. And I just wanted to acknowledge all the people that have made this mission possible, looking at all the proposals. I'm so excited for all the amazing science that's coming our way in the next few years. So I really appreciate the many, many years of work that have gone into making that happen by a whole multitude of people. And finally, like I mentioned at the very beginning of my talk, looking even farther into the future, I did want to mention that this decadal review for astronomy just came out on Thursday, hot off the press. And I wanted to highlight just a couple of recommendations. So this is a community effort where astronomers can submit white papers suggesting this is the topic I think is important. This is how I think we should spend money to study the universe. And the report recommended kind of many things, but two key things I wanted to highlight was participation in a program of extremely large telescopes for the US. And so the reason this is necessary is right now we're sort of in this regime of planets characterization, so accessible with transit techniques, like I said, habitable zone around cooler stars like the M dwarfs or TRAPPIST-1. But if we really want to go out farther, this will be possible with this extremely large telescope program. And this would really provide capabilities that you can't get in space and we don't have yet on the ground. And so this would be composed of the Giant Magellan Telescope, which is planned for construction in Chile, and the 30-meter telescope, which is planned for either construction in Hawaii or in the Canary Islands. And then the second component that I wanted to highlight is really even farther in the future. So that's really like 2030s. That's the actual decadal part. Going a little bit further, the survey recommends a large 6-meter diameter infrared optical UV space telescope with high contrast imaging and spectroscopy to be able to search for biosignatures from habitable zone planets, as well as do lots of other general astrophysics. And this was from Twitter, there were 4 mission concepts proposed in this decadal. And these two, Habex and Louvois, they're sort of suggesting that something in the middle be what's pursued. So that will go through a lot of mission and technology maturation. So still a long way off, but it's really exciting to see the community come together around these goals. And there's lots more to read about, including lots about state of the profession. And so I encourage you to check out the full report at that link. And I just wanted to end by, if you take nothing else away from this talk, one thing the report says is that astronomical activities do not occur in a vacuum, disconnected from other global concerns. To the contrary, how and where astronomers conduct their work can both endanger and be endangered by the rights and activities and concerns of others. Indeed, some of these concerns rank among the most pressing global challenges of our time, from climate change to human rights. And consequently, the future of astronomy, like the future of so much of the world to which it is bound, will depend on the development and implementation of more sustainable practices and partnerships with the global community, commercial ventures, and Earth. And so with that, I will end, and I'm happy to take questions. Thanks for your attention.
That was awesome. Thanks so much. You have so many great visuals.
Thanks.
The animations and stuff are amazing. Let me see here. Okay. So yeah, a couple of questions. With regard to JDBST, what are you most excited to see come from that? What is there a specific result you're really eager to get back, or something you'd be surprised to see?
Yeah, I mean, I'm super excited for my program because I think what sort of sets it apart is that our goal is to not just understand the planets individually, but really as a population. So, but that's biased. So setting that aside, the TRAPPIST-1 system, like, it's hard to get more exciting than that. It's 7, rocky planets. Many of them could have liquid surface water, and we're just going to get an unprecedented view of these types of planets around another star. And so, yeah, reading through a lot of the proposals again, there are multiple proposals, and just that whole program to really characterize that system. I'm really excited to see what that produces. If there's variability between the planet atmospheres, so it'll be amazing.
Do you have, you mentioned the possibility of detecting eruptions on some of these worlds?
Yeah.
Anything about that? Could you say more about that?
Yeah. So especially, I mean, we discussed that in our proposal. More like earlier interactions between the atmosphere and interior, and how that might have influenced the composition of the atmosphere. But especially for those like hot rock planets that are really close to the star, they shouldn't have any atmospheres. Those should have been evaporated away. And so if any gases are detected, it seems likely that those would be coming from the interior of the planet. And these planets are also really, really close to their host stars. And so similar to Io, are maybe experiencing really intense tidal forces that are like squeezing and expanding the planet. And so might be actually really good sites for trying to detect what's coming out of volcanoes on another planet.
Yeah, and then thinking of the future, you had sort of mentioned, aspirational science. What do you think of the realistic timeline for us to detect life on another world? This is a question that people always want to know. What do you think?
I know. Yeah. Well, I mean, now this report kind of does put a timeline on that. If we're gonna, so it could. The telescope that really would have the capabilities to do that is something that would launch in the 2040s. And it would be really more than just an indirect detection like the transit method, but it would literally taking a picture. It would be like the blue dot photo for another planet system. And so that is coming in the 2040s. There's a lot of technology development to do to get there. But I think that is a realistic timeline. I'm not involved in any of the mission concepts, but I would think that people involved would say the same. And so, but there are there's maybe two other things to mention. One is that we know that small planets are common, but we don't really know how common Earth orbit around solar type stars, how common those planets are. That's what Kepler was trying to determine, but it didn't quite get there due to some technical difficulties. And so it may be that we do a survey of 25 planets. That's what this decadal report recommends, and we don't find anything. But then we would know that that's enough to know kind of how common Earth-like habitable conditions are. But there's also stuff that's happening between now and whatever mid-2040s, which is all these characterizations of planets around M dwarfs. And those are very different environments than around our sun. But life on our planet is very diverse and forms in weird and surprising ways and places. And so I think there's a lot to look forward to between now and the 2040s as well.
You know, it's 2040.
I know.
For ahead.
We got to make it there.
Yeah, so here's a question. Since the gas giants of our solar system take decades to orbit the sun, would we be able to detect similar exoplanets?
Oh, that's a great question. So probably, basically not using the transit technique, just because it also, as the planet gets farther away from the star, the chances that it crosses in our line of sight goes down. But giant planets have been detected with other techniques. So one of them is that radial velocity technique that I mentioned. It takes a decade to monitor that type of planet and find it. And so that really takes a lot of dedication and institutions and funding agencies who are willing to support that kind of work. But there's another method that I didn't mention that's called direct imaging. And that's more sensitive to planets that are farther away from the star. They have to be well enough separated that you can literally take a picture of them. And there have been some giant planet detections using that method. It is hard to suppress the light of the star. So it's technically hard to do, but there are new systems that are pushing those limits even farther. Most of those planets are also fairly young that have been detected so far because they're still sort of self-luminous, so they're easier to spot.
And then one last question. You had such a lovely story at the group meeting today about what prompted your interest in astronomy. So I'd love you to share that a little bit with the audience here.
Sure. Yeah. So, when I was in school, I liked lots of subjects. I actually thought for a while I wanted to be a science writer and work for National Geographic and travel the world. But when I was, I think I was 11 when the movie Contact came out with Jodie Foster. I saw the movie before I read the book, actually. And just seeing that, and seeing a woman scientist, and she really kind of sticks to her guns in the film, and follows what she thinks is the right thing to do. And the film is science fiction, so she finds evidence of life. But yeah, that was just really inspiring to me, and I saw that, and I was just sort of like, yeah, that's what I want to do with my life. That sounds great. And so very much, I have different science questions that I'm interested in, but what gets me up in the morning is are we alone? So, I mean, honestly, the fact that could be answered in my lifetime is pretty phenomenal.
I mean, yeah, it's hard to believe. Certainly the questions about life elsewhere in the universe have been asked for thousands of years.
Exactly.
But to think that we're on the verge of that. And to that end, I have one more question. I'm going to give you. Justin asks, will JDBST's atmosphere readings be precise enough to detect the fractional scale levels of biosignature gases, the atmospheric imbalances that metabolic life might cause? So he's talking about detecting the sort of biogenic atmospheric signatures.
Exactly. Yeah, it depends on the planet and how the specifics of the planet and sort of how high of signal to noise that detection can be. But yes, in some cases, that would be what JDBST would be able to detect. For example, in that K218b case, even though that's not a terrestrial planet, that paper simulation that I showed suggested that JDBST observations would be able to detect chemical imbalances in the atmosphere that could be signatures of life. So the answer is yes.
Yeah, just amazing.
I know.
Oh,
everyone keep their fingers crossed in December.
Well, great. Well, thanks so much, Dr. Teske. That was just excellent. Really enjoyed that. Again, thanks folks for tuning in. This is Boise State Physics First Friday Astronomy. Let me get you to stick around just after this, Joanna. Join us again in December, on the first Friday of December, which is, let me check and make sure to give you the right date here. December 3rd at 7:30 p.m. Mountain Time. We're going to have Tyler Gordon come and talk about his work looking for exomoons. That should be really interesting.
Oh, very cool.
Yeah. All right. Thanks, everyone.